All right, here we go. 2 units left. This is our unit on acids and bases. So I'm going to have a little bit of theory here at the beginning, and then we'll work on maybe some problems later, maybe in a different video. I don't know, but we'll see. We'll figure it out as we go, right? So acids and bases is what we're going to talk about, and in picking the background, Microsoft called this the ion background, so I thought it was appropriate for chemistry. I might switch it up in the future, but I'm always thinking about you guys. We did talk about acids and bases earlier in the year, so this is a little bit of a review to begin, but remember that acids produce or increase the concentration of H plus in solution, and bases produce and increase OH minus in solution. And we did talk about Bronson-Lowry acids and bases and the conjugate acids and bases, but in a reaction they are proton donors, acids, and bases are proton acceptors. Remember, H plus is hydrogen. Hydrogen has one electron, one proton. If I lose that electron, I become positive, and all I'm left with is a proton, and that's really the basis for these definitions: proton donor, proton acceptor. Hopefully that is stuck at this point. If not, by the end of this unit, you should understand H is an acid, OH is a base. All right, so you're going to have strong acids and bases and weak acids and bases. We're going to talk about both and buffers and whatnot, but a strong acid, what that means is 100%. Last unit we talked about equilibrium. There is no equilibrium here. You have an acid or a base, you put it in water, it is 100% coming apart into its constituent ions. This is my acid, A for acid, H for the hydrogen that's there. All of that acid is going to break apart into the anion, acid anion, and H plus for the cation H, right, the acid part. This can be written in two ways. You'll see it written in two separate ways. You'll see it as kind of like just the acid by itself, which forms H plus, and then the anion. This spoke earlier. A is anion, not really acid. And then H, you'll see it as a reacted with water. You see it this way as well. This is an acid-base reaction as well. Sorry, man, I messed that one up, but can't back it up and correct it, so it's just going to have to roll with it. These are just acid reactions right here. So this acid mixing with water, you'll see it forming H3O plus, hydronium. This is also can be represented, and so I'll show you this is kind of representative of an acid. You'll see it written as H3O plus or H plus. And then we always have this little guy, this anion, sitting to the side. Having all kinds of problems today. All right, so acid and water, H plus, A minus, strong acid, 100% dissociation, which makes these problems a little bit easier. Then I have a base example here. Bases are going to dissociate 100% that are strong to your cation, Na plus, and your anion will always be OH minus. So again, acids, H plus or H3O plus, bases, OH minus. And whatever we say about acids will apply to bases as well. If I'm talking about H and H plus, usually you can translate the H and make it OH minus in the same, the same concept. They work hand in hand. You should have your strong acids and bases memorized. It was a pain for me to type in on PowerPoint all of these subscripts and superscripts and stuff, so I'd copied this. But really, I mean, nitric acid, sulfuric acid, and perchloric acid are kind of the odd man out. And then these guys are the halogens. They're all strong, but HF's a little bit weaker. But the main ones you find are hydrochloric, nitric, sulfuric. That I wouldn't be surprised if the College Board threw this at you, perchloric acid. But hey, memorize this and you'll be fine to know that the strong acids. Strong bases, you don't really have to memorize a list. If you just remember groups 1 and 2. the alkaline metals and the alkaline earth metals are going to form strong bases. They might not be 100% soluble, or their KSP values may be lower, but they're going to be strong bases. When they are in water, they are going to be 100% associated. And that leads us to water. Water is a big part of this, and the basis for the scales to use to measure acidity, basicity, is based on water. So you have the auto-ionization of water. And so water just by itself, you see this read two different ways. Again, I couldn't find the symbol for equilibrium in PowerPoint. It's annoying, but we'll just have to deal with it. H2O, H2O can combine to form H3O plus and OH minus. So one of these guys is going to donate H to the other one, and one becomes acid, one acts as a base. And then the other way to see it, you'll see it written as H2O. I'm splitting almost to H plus and OH minus. And that leads to some important concepts. And I'm going to draw and show you here in a second. All right, so here, kind of continuing what we were talking about, the auto-ionization of water. It was a pain for me to write in PowerPoint, but I did leave these subscripts off, the liquid, aqueous. But we can, this is an equilibrium expression, so we can write this as a K. And maybe. All right, there we go. We'll do it, make it a KC for now. All right, and you can pause the video and try it on your own if you'd like. So then I have H, the concentration of H plus, times the concentration of OH minus. Nothing too bad. Now, this K has a value. That value is 1.0 times 10 to the minus 14 equals H plus times OH minus. And this K actually is K for us, KW, product constant of water. I wrote this kind of sloppily, but 14. Hopefully this minus 14 rings a bell. The pH scale is based on this. It is from, 0 to 14. I mean, we can go beyond this, but typically that's the range we're going to find things in. And for you math nerds out there, you might know what this lowercase p is. I know you're all shouting at your screens. I know what it is, right? That actually means the negative logarithm. Lowercase p is negative logarithm. And this capital H is really the negative logarithm of H plus is pH. If you take the negative log of 10 to the minus 14, what do you get? You get 14. It's kind of nifty. Scientists don't like these really small, really large numbers, so they introduced the log here to make these numbers for the pH scale a little bit easier. But you are dealing with really small quantities, right? 10 to the minus 14. So with this expression, the concentration of H plus times the concentration of OH minus always equals 10 to the minus 14. So if my H plus is 10 to the minus 7, and what must my OH minus be? Why? 10 to the minus 7. What is the neutral pH? Neutral pH is 7. So when they're equal to each other, we now have the neutral pH. It's neither acidic nor basic. Now, one thing to keep in mind with the pH scale, as my acidity goes up, well, as my concentration of H plus goes up, right, say 10 to the minus 4, right, the concentration of that, the pH of that would be 4. So my pH scale would go down on the pH scale, but in reality, I'm actually increasing the H. But if it's 10 to the minus 4 for H plus, my OH minus concentration is 10 to the minus 10. Right, that's gone down. And like I said before, anything that I say about acids works the same way with bases. There is the other scale called the pOH scale. Same thing, 0 to 14. But in this case, it's the negative log of hydroxide. So in this scale, a base is in the lower range from 0 to 7, and acids are from 7 to 14. And I'm running out of time here on my video, but that's the basic, and I'll probably give you some problems on this. Hope you enjoy. Subscribe and like. Enjoy your day.